Interesting. All right, I think we should start. Basically, I prepared for the end. I mean, until the end for the lecture already. So the pathway to end this course is we will do countability, separability, okay, and then we will do a recent lemma, a recent metrization theorem, and do Tikhonov theorem, and then we will end with before Tikhonov theorem, we will do a bit of storm check compactification, and then finally we will finish with Azoli. It's the same, I think. Azoli theorem, okay, the most general version, and then we will end this course. All right. So before jumping into the first to the countability, let's recall these two very important concepts here. Okay. So what's the limit point in topology, and what's it means for a sequence to converge in topology? So remember, in topology, we might not have metrics anymore. Okay. So we need to talk about open neighborhood. Okay. We need to talk about open neighborhood or the open set. Okay. What is not open neighborhood? It's just an open set that contains some point. Okay, neighborhood of x. So the open set should contain x. So when is an x a limit point? If for every neighborhood around that point, around that limit point, intersect a. So when we talk about limit point, you need to talk about limit point of what set? Okay, limit point of what set? So x is a limit point of a if every neighborhood of x intersect a in some other point other than x itself. So you can think of this neighborhood help you to isolated some other point in a rather than x itself. Okay or not? Okay. So this is a this is a limit point. So how about convergence? Okay, convergence. So what converge? So you need to look at a sequence of point, okay, in your topological space. So we said that a sequence of point converges, okay, to x if for every neighborhood of u, okay, there exists a large n such that for all little n greater than n, xn is in u. What does this mean? What does this mean? Can you imagine a picture out of this sentence here? So if you want to say a sequence converge to a point, okay, you make a open neighborhood there. And then what happened? There exists a n such that for all the terms behind this capital N, it lies inside the neighborhood. Make sense? Okay or not? So like last time we said, right, this x here we call limit. This s we call limit. And limit point is different. Okay. Remember the example, the constant sequence example. Okay. Limit and limit point is different. All right. Last time we were a bit confused with this proposition here. This proposition says what? There's one very useful point that we keep using is this point. If x is a limit point of A, then every open ball centered at x contains an infinitely number of points from A. Note that these theorems are put in where? What's the assumption here? What's that x? X with a D is a metric space. Okay, so this is a result in the metric space. But maybe in topology, not quite true. Okay. But for sure, from the definition just now, you can find one element which is different from x, but not sure if there's infinitely many of them. Okay. So let's return discussing the thing that we left last time. Oh, okay. Another thing is, before we jump into today's stuff, we also have description of limit point in topology actually. Okay, so you can recall these two theorems here. So when are you a limit point of your set A? Okay, if every open set U containing X intersect A. Okay, so this is almost the definition. The other thing is you can talk about basis element as well. So you can reduce talking about every open set to talk about every basis element. That's all. Okay, so this is the two theorems that we describe when is a point inside the closure of A, or in other words, it is a limit point of A, or in A, both case. Okay? Okay or not? So this is the only description of a limit point in topological space. Okay, so please don't confuse. Please don't confuse between the two. Okay. All right. So let's return discussing the theorem that we left last time. Before that, let's recall what's the definition of a first countable space. So what's first countable? What's first countable space? Any idea? Please go and check definition. What is first countable? What is first countable? If every point, so every X in X has countable Cs. So now it turns to the question then, what does it mean by you have a countable basis at the point? What's the definition of having countable basis at a point? Okay, so X topological space has a countable basis at X if there exists a countable collection of open neighborhood whose open neighborhood is this of X such that for every open neighborhood of X, say, let's say I call this U, there exists B in B such that B contained in U. Okay. This B need to be unique or not? Not need, just existence is enough. Okay. Okay. Can you see that why we call this basis? This line is like a basis property, right? Okay, you can find for every open neighborhood, you find one element that sit inside this open set here. And obviously both of them contains X. Okay. Yes. The B is on X. Yeah, exists a countable B. The B is. What do you mean by B is a countable? Basis for topological space. Then you need to check the wait. No, I mean this one is just this. I mean, how to say? So are you claiming that? So if I consider, okay, so you say that if I have this countable basis in every X, and then I can take for every point, I take this countable collection of. So let's say if I have my space is first countable, and then for every x I can take this countable b, right? And then you want to take union of all these things, is it? And then you want to check whether this is the basis for the topology you started with. And you can try and think about it. So you want to think about it together, or you want to try yourself? I think it's a valid question. Seems like it, yes. You just need to check the two property. Oh. Is it true property? What's the two property? Yeah? For every x, you have a basis element that contain it, is it? First one. So obviously, yes, because you take a countable collection of them. And then the other one is between two intersection, there is a smaller one that contain it. I think it's okay because by this one, if you take intersection and then because the open neighborhood around that point, then by this property here, around that point, you have a countable neighborhood. Yeah. Yeah. I think works. Yeah. So if your space is first countable, and then you go and take for every point this countable basis, and then you take their union, should be your basis of your topology, I guess. So you can see that in first countable, this basics like looks a lot. For every point, you have this countable connection. But in the second countable, remember what's the second? Hey, have I introduced second countable? Okay, not yet. Okay, later we'll introduce. You'll see that second countable is maybe it's more restrictive, but it's how to say more restrictive, but yeah, but the basis is less, more or less than this first countable. Okay, we will see later. Anyway. All right, so we have defined what is a countable basis at a point and then first countable. So why we are introduce this first countability here. So there's one point here is so let's put the idea here first before we introduce the theorem again. So with a first countable space, okay, really you just need to use convergent sequences, okay. Let's use convergent sequences to have, for example, limit point of a set, okay, and to check continuity of a function. Okay, so let's see what this two sentence means here. Okay, so let's reintroduce the statement we have last time. So consider a topological space X, right? And let A be a subset of a topological space. Okay, if there's a sequence, okay, if there's a sequence of point Sn that converge to X, okay, when n go to infinity and Xn is in A, then X is in A bar. Okay. And the other direction is true. So if you have a point in A bar, if your space is first countable. Okay. Meaning if your if you are limit point, okay, of your set, there exists a sequence that converges to you. Okay. B, okay. So talking about the continuity. So normally how we check, so what's the necessary condition for continuity? That is if f is continuous, okay, then for every convergence sequence in X, okay, fxn will converge to fx. Okay. Not that this one, this statement here is similar to what you have in metric space, right? But now we are working on topological space. Okay, later we will try and show this. And the converse is true if X is first countable. Okay. So what's this converse here? So if you can check that for every convergent sequence Sn, okay, in X, you have fxn converge to fx, then you would know that your f is actually continuous. Okay. The other direction is true. Okay, so let's quickly run through again the proof last time. So last time we discussed A halfway, right? Okay, so let's do the normal way first. Okay, let's prove that if there's a sequence that converges to X, then X is actually in A bar. But but what do we have here? So I mean, what do we have here? So for every convergence, right? So it means what? For every open neighborhood around X, there exists an N such that for N greater than N, all the term behind capital N is in U. Is it enough or not? What is the definition of limit point? You need at least one, right? But this Sn, where are they from? From A. Okay. Yeah. Okay. So this Sn is in A. So X is in A bar. Okay, how about the other direction? So the other direction we kind of stuck last time, right? So if you have a limit point in A, okay, and your space is first countable, how on earth you are going to construct a convergent sequence, okay, that converge to X? Okay, how do you construct it? Okay, last time we have some idea of intersection, okay, but we are not quite sure what to intersect, right? Last time. So let's take since X is countable, first countable. So take out these countable basis. Okay, I call it a countable basis. Basis at X. Okay. So the point here is we will define Xn, okay, such that this Xn here live in the intersection of first and bi. Okay, first and bi. Okay. And Xn is not X, of course. Okay, because X is a limit point. And so are you worried that this intersection is empty or not? No, right? Because it's just finite intersection. So finite intersection is still an open set. So you can still use the definition of limit point here. Okay, so you can still find a point other than x. So, so what you need to show now? So you need to show now this xn converge to x. Okay, xn converge to x. So how to show Sn converge to x? You need to check for every open neighborhood of x, there exists an n. Okay, so how to find this n here now, such that uh, for little n greater than n, Sn is living in U. So the problem here is how to find that bit n, so that all the term behind that n live inside U. Yeah, good. So we can use the first countability at x. Okay, we can consider the first countability at x, so that you can find a Bn such that this Bn here live inside U. Correct not? This is what the first countable tells you. Okay, for every open you can find a member in your countable basis. But why is this enough? Why is this enough? Huh? Why is this enough? Why is this enough? Every intersection of what? Yes, correct. So if you consider for little n greater than n, Sn that live in the intersection from 1 to n, Bi surely live inside Bn. Okay, and then Bn live inside U. Okay or not? You take more, if you take more intersection, Bn is already in there, right? And then if you take more intersection, then this intersection here will live inside. Correct or not? Does it make sense? Okay. So for all of them, you should live inside Bn. So Bn live inside U. So every term behind capital N live inside U. Okay or not? As long as this intersection contain Bn, then you are good already, right? No matter how many things you add more. Yeah. Okay, so this is the part that we missed last time. So, hey, remember why we missed last time? This is like how you do, like why you spend long time doing assignment. Right? So the point here is you need to first get the right way, right construction first. Then will make your life easier. So if you make um, I say not clean construction. I wouldn't say it won't work. Some case it works, but it works in the way that you need to make a lot of justification. Okay, does it make sense or not? Okay, I wouldn't say it won't work, but it's just that not clean. Okay, yeah. But sometimes this is actually normal, in the how to say, in the research in the research in the research process, you will meet this kind of how to say, not clean construction. Then you will ask another question. Then how people give the clean construction here? So in the process of cleaning up your own construction, right, you might find a more, how to say, 优化, more how to say, simplify, optimize, yeah, more optimized way, okay, to explain your idea or your construction, okay, optimized way. But this is quite general happening in the frontier research field. For example, they want to prove a theorem. Oh, I got 100 pages. Okay, 5 years later, this 100 pages reduced to 50 pages. And then again, 20 years after, reduced to 25 pages. It's normal actually. Okay, but when I say it's normal, that means you actually need to go through this process. You cannot take for granted, you know. You know what does it mean by take for granted? 懂什么意思？什么是 take for granted？什么意思？What is take for granted means? Yeah，理所当然，非常好，很好的翻译。不要以为很理所当然，你知道吗？没有啊，没有事情是理所当然的，我告诉你。哦，全部东西要自己 work 出来。OK，没有天下没有白吃的午餐的。OK，yeah，OK 了。好啊，我以前也是像你们啊，你怎样找到这个东西的啊？你怎样找到这个东西的？没有人是一下就找到的，有可能啊，但不是每一次。哦，但是可以确定的是，most of the time 我们都是 hard work 做出来的。哦，yeah，就是 go through 一些 correction 啊什么这样才会出来。Most of the case 我可以保证你。OK，偶尔一两次啦，有这样的东西吧。Most of the time，我们都是 hard work 做出来，这才是数学啊，数学的本质才是这样。虽然我们每次给你们看的都是很简短的答案，很简单的答案，真正数学不是这样做出来的。好，OK，要算很多，算很多，算很多。不然你看不到东西啊。你以为做两题啊就会有看到东西，不可能的。你看到那个东西是假的，为什么是假的？因为我换一下你就不会做了，我换一点东西你就不会了。啊，那东西是假的，真的东西是什么？有一点像在你们去比那种 Simon Moraes 的题目那种啊，就是我乱随便给你一题，OK，如果你知道 concept，你懂用什么，哎，等你就会做哦。但如果你是那种做题那种奥数那种，做一大堆，做一大堆，做一大堆，你只是做题机器吧，哦，你不一定知道它里面用的是什么。你一知道里面用的是什么啊，管它讲遍你都会做的，是这个意思，OK 吗？好，OK，B next part。So what is B? So first of all, we want to show that if f is continuous, then give you any convergence sequence, the image of that convergence sequence also converge. Okay, converge to fx as well. Okay, so let's quickly run through it. One direction. Assume that f is continuous. Okay? So given convergence sequence Sn to x, okay, what we want to show is we want to show that Fsn converge to Fx. Okay. But here there's no d or there's no like for every epsilon then if n greater than n then this distance less than epsilon. But what do we have instead here? Instead of epsilon, we replace epsilon by open neighborhood. Okay. So in this case here, random epsilon become a random neighborhood. Okay, we need to talk about random neighborhood at fx. Let's consider random neighborhood of fx. Okay, and then it's very similar to the epsilon delta proof, right? So we need to play around with our delta. So in this case here, delta become the inverse, okay, inverse image of this v here. So we can see that the inverse of v is what? Is also an open neighborhood of x because this is the definition of f being continuous. Okay, the inverse is open as well, right? So how do you remember this? In epsilon delta proof, so you need to make sure that fxn minus fy is less than epsilon. So less than, that one is strictly less than. So that's why we have an open ball. Delta side is also strictly less than. So also is another open ball. Okay. So here this is imitating that definition there. So in this ball, what happened? We know that xn converge to x. Okay. So from this part here, there exists n such that For all n greater than this n, Sn is in F inverse V. Okay, so this also implies that Fxn is in V. So the same n works that prove Fxn converge to Fx. Okay, so to appreciate this proof, I want you to connect this proof with the metric space proof. Okay, try and link them together. Okay, yeah, yeah. Okay, so this is just an upgrade version of metric space proof, but the real thing is this the other direction here. So assume x is first countable and fxn converge to fx for all convergent xn. We want to show that f is actually continuous. Okay, I mean, to show that f is continuous in topological space, there are few equivalent definition, right? Okay, so we will instead use that f of a bar is in f a bar. Okay, we will use this. Okay, so to use this, so let's take, so we're going to show that f of everything in a bar is in the closure of Fa. So let's take to this end, so let's take x in a bar first, and then see what happens we apply f to it. So s in a bar, what does it mean? By a, what do you get? There exists a sequence that converge to x. Okay, because we assume first countability already. Okay, we can use a. Then by assumption, what you get is fx, sorry, fxn will also converge to fx. Where's this Sn from? Yes, good. So fx, in other words, fxn is living in fa. Okay. We close. We close. So this is the by part A again, right? By part A again, how do you tell you are in? How do you tell you are in the closure of a set? Okay. By A again, fx is in fa bar. What is A again? So A says that if you have a sequence, okay, that converge to you, okay, and then all the term in the sequence in A, then x is actually in, then you are actually in the closure of A. Okay, so you found a sequence fxn, okay, which is in fa, and fxn converge to fx. So this fx here should live in the closure of fa. So using A again. Okay, so hence fa bar is in, sorry, f of A bar is in bar fa bar. Okay, so done. Okay, so far any question or not about this two theorem here? No. Okay, let's keep go on. What's the nice thing about first countability here? So there's another theorem says that if you are first countable, okay, and every convergence sequence, okay, has a unique limit, then Actually, X is Hausdorff. So to be Hausdorff, you can satisfy this sufficient condition. Okay, if you are first countable and then every convergence sequence has a unit limit, then X is Hausdorff. Right. Any idea how to prove this? So to show that your space is Hausdorff, what do you need to do? 2 point, you need to find an open set such that they are disjoint. Okay. Why? Not satisfying. I mean, Hausdorff space is just like that exists, right? They also will have some open set, maybe also have non-intersection. But as long as that, for every Hausdorff space is that exists or for every that exists, all right? Only that exists. Oh, that exists. So maybe there are open set that contain the two. Right. Okay. So I mean, we can argue by contradiction or contrapositive. Right? Suppose X is first countable. Okay, we will show that if S is not Hausdorff, then you would have a convergence sequence that has different limit. Okay, this is quite different with what we always met before. What we met before in metric space, we always has unique limit there. Okay. So to this end here, so because it's not Hausdorff, right? So meaning, let's see how we cook up this convergence sequence here. Okay, let's see how we cook up this convergence sequence here. So since it is not Hausdorff, what happened? There is this 2 point such that every every open neighborhood of A uh, and every open neighborhood of B such that U intercept V is not empty. You know, okay. So what happens here? So suppose we have some nice collection of open set to work with, right? Because our space is first countable. So we consider the countable basis at A, basis at A, and also the countable basis at B. Okay. So have any idea how to cook up a convergent sequence here? We actually did do quite similar construction just now. Okay, where you can pick xn to be the intersection of 1 to n that is of the intersection of Ni intersect Mi. Okay, so from N1 intersect M1, you take 1 point out. And then the next term, you take N1 intersect M1 intersect N2 intersect M2. And then you keep going. Okay. So now you need to argue what? Why A and B is the limit of this Sn here. Okay, so in other words, why this Sn converge to A and B. So you need to show a conversion to A and B, right? So let's talk one of them first. Okay, let's talk about A. Okay, let's talk about A. So you want to talk about convergence to A, right? What do you need to do? For every yes, not yet. For every open set contains A, there exists a N. Okay, there exists an N. There's an N. Okay, there exists an N. Should I write in this way or not? Should I write it? Okay, there's this an N. Okay, I don't want to put this N first. I don't want to confuse the neighborhood N. So there's an N such that what? Hmm. Wait. Where are we? So we want to talk about convergence at A, right? So what's the definition of convergence at A? For every open hood at A, this such that for every little n greater than this n, it is living in this neighborhood here. So how to find that capital N now? Ah, same trick, right? Same trick what we have just now. For this open neighborhood U, because our space is first countable, that means there exists an Nj. Okay, this N is not the number N. This N is my countable basis. Don't confuse it. So this Nj here will live inside you. So in this case here, what can you do? This little j is the capital N you want. So for every k greater than j, sk is living in the intersection of from 1 to k, okay? And surely this intersection here will be living inside nj, and then nj live inside you. Okay, make sense? So similarly for B also the same. For every open next set containing B, you will have some Nj, correct? Yes, good. Nj. So therefore, for all k greater than j, Sj is living in Mj. Mj living in U. Yeah. Yeah. So this says here similarly, Sn converges to B. Any question or not so far? So this is how we use. So throughout this three proof here, you will see how we use this first countability here. Okay, you will see how we use first countability here. So far, okay, about first countability. Okay, let's go a bit further before we break. Okay, so we'll continue with new definitions. So you'll see if a space or a topological space has a countable basis for X topology, then we will say that X is second countable. Or we say that it satisfies second countability axiom. Okay, it is second countable. So when we talk about second countability here, For all the bases you need for a topology is just countable. Okay, countable is what? Finite or denumerable. Okay, finite or denumerable. Okay, so if you do the construction we did just now, right? For every point, you have countable thing. Okay, so for every point could be finite or denumerable. And how many points in your topological space? Maybe finite, maybe denumerable, maybe uncountable. Okay. So in this case here, I don't care how many points in your topological space. What I claim here, if you are second countable, then I just only need countable bases to generate your topology. Okay or not? Yeah. Okay. So you can see that which one apply which one implies which. Does first axiom imply the second one or second one imply the first? Okay, why? No, you can compare with talking about what do you mean by a point? I don't get what you mean. Okay, can you like uh Urai, can you explain more? I mean you need to argue from the definition, right? Okay, so you need to argue why if you say that a second countable implies first countable, so what is first countable? At every point, you need to have this countable collection. So yeah, if I give you the second countability here, how do you give me the countable collection there? How do you construct for me? Huh? Ah, yes, yes. So if I have this countable basis here, I want to show that there's countable collection at that point. What do? I just consider the basis element here that contain that X. How many of them you can get? At most countable, at most. Then it's also countable collection. Okay or not? Does it make sense? Okay. Yeah, so second countability would imply the first countability. So remark here, second countability. Yeah, let's give some example and then we will take a break. Okay, so first example is this second countability seems quite strong. So what sort of space satisfy this property you think? But it's quite normal to the space that we studied before. When we talk about countable, what's the first thing you think about? Yes. Wait, natural. Okay, yeah, rational number or rational number. Okay. So can you use this number to build some space or not? Okay. Huh? What space? Euclidean topology. Okay, or you just consider R. Okay, is R second countable or not? No, eh? You sure? Can we use countable basis or not? What's the basis of Euclidean topology of R, for example? Good, open interval. Can we have just countable many of them? Huh? Can, right? So we just simply take open interval AB such that AB are in rational. Can cover all, right? our rational is dense. Okay. Yeah. So we just need countable basis. So similarly, you can like what Ziqian said just now for general Euclidean space, it is also second countable. For this product space, you just take product of this rational open set. Okay. Surprisingly, if you go infinite, it's still second countable. Okay, if you go infinite, it's still uh, second countable. Okay, it's still second countable. Okay, okay. So any question before we take a break here about second countable, first countable? Question before I take a break. If no, let's take a break until 102. It will resume the 102.
呃，就是有个 sequence，然后要满足这个条件，就是这个 sequence 要去对，有一个 sequence，我现在 create 一个 sequence，我 define 一个 sequence，我需要去证明它 conversion。
它是不是 sequentially 那他问要不要 prove 这个？我没有 prove 啊。
有什么好 proof 这个？叫你找这个 proof 里面哪一句话不会连哪一句话？
所以他给 contract number 的时候，
怎么？哦，你要搞，你可以看到什么给谁？给哪一句话？哪一个 implication？
对，
给哪一句嘛？就是这一句去这一句啊。
然后整等于 n，
你说这句去这句有问题了。
啊，
OK，然后你现在要做什么？给 counter example。
好
OK，然后 counter example 是你要找一个，你要找一个 sequence 没有 convergent subsequent 的 sequence such that 没有 open neighborhood content 放在里面有，这个意思。找到了，
我找到了，它不 converge 这个东西。
它也没有 convergent subsequent。
嗯
OK，然后这个活在什么世界 ？N，然后它的活界就
反正
of finite。然后你是要证明是每一个它的 open neighborhood。嗯，infinite limit。OK，然后
没
加
我需要去证明它没有 convergence sequence。
要啊，刚才不是问你哦，要啊，
要证明它没有 convergence sequence，就是要证明它不是 convergence。
不是错，sequence compare 是要每一个，你只是一个吧，你只是没有，你不是这个意思，不是这个意思，你要真的是这句话去这句话吧，你怎么要推到这句话？
因为就是这个 sequence，
对，
我证明它没有 convergence。
就好了吗？怎么你推到这句前面了？也就是这个去这个不成立就好。他这题目只是叫你去找哪一个借哪一个是不对的，但他整个 proof 就错了哦。诶，不会难吧？应该跟你正它为什么不恐怖是差不多一样的，因为你这个都已经一直上去了嘛。你如果不选其中间的一些东西，它还是一直上去啊，但是一样的跟你说的方法。诶，因为你这个在哪里实践啊？跟 metric 还是在
Topology
Topology 啊？因为你前面会有一个 n such that 什么啊？every Sn 大于一个号码，然后后面也是一样，你也是 subsequent 化了。
假设还有一个 convergence，
OK，
然后所以就是它里面去到一个 L， 然后
成立咩？这边有什么？
假设
这是 topology 哦，这个是 topology 我们这样写。
topology convergence
对啊，topology convergence 是那个 open set 的东西。
那个 feature，
啊，就是每一个 open set
每个我
在哪里啊？这九就我刚才有抽出来做那个 revision。
这行对，这行下来抽第三，是我可以这样，这小波是我可以这样说。
没有，这个是选
哦，当然。
第三是哦，其实这是第一个，这个第一个 这个跟这个没关系，这个只是说吧。第OK 有一个所以就是有一个大 N 或者或 SNK 大过 N 这个 SNK 还是在这个 unit 内。可是，在 combined topology 里面，这个 finite
好，
所以我可以 denote 这些东西。
嗯，
所以在它的大过它越来越大的时候，大过 N SNK 它不对每一个然后我看
你要到哪里去？
然后就一个班才有每年的三十，所以跟我想法有没有？他在这里，可是他在大的时候，他就不一定在有里面的。就是你讲的在上升，在上升，在上升啊。就是我现在有的是，我后面这个跟前面是翻那个可是到这个后面就是引翻那引翻，引翻那，我这个它引翻那个，然后我剪掉前面几个翻那的，它还是引翻那。
然后又怎样？又怎样？又怎样？我看不到又怎样？你再想一下，再想一下。Hello. Okay, let's resume. Okay, talk about second countability. Yeah. Okay. So let's define some more terms here. A topological property is hereditary if whenever X has the property, then every subspace also has the property. Actually, you met this kind of situation before. What you meant is some topological property is not hereditary, right? Which property is not hereditary? Which one? Huh? Close. Yes, close is not hereditary. Close is hereditary if your subspace is closed as well. Hey, wait. That one is the other direction. That one is a close in the closed subspace is closed in the larger subspace. Right? I mean original space, right? This one is if your X has a property, then your subspace also has. Say not say meaning S has this property, but subspace doesn't have it. Am I wrong? Huh? If not having this property means what? What am I thinking is that if X has this property, then subspace doesn't have it. Yeah, also works. Okay, yeah, good. Okay. How about another one? Connected. Sure. Rostov. Rostov cannot have Rostov work for all X, right? Also work for all X or XY. What else? More recent one. Recent one. These are the topological property. Compactness, right? If you take closed interval 0 to 1 and open interval 0 to 1, it's not compact. Okay. And the other topological property, I will say that it is productive. Okay. Productive here is not produce a lot of things. It's just about product. So if arbitrary product of spaces with the property also has the property. So you can ask like, is product of Hausdorff space Hausdorff? Something like that. Okay. It's a product space of Hausdorff space Hausdorff. Both okay. Try and show it. So the claim here is both first countability axiom and second countability axiom are hereditary and productive. Both hereditary and productive. Okay. So how do you show? Let's say we want to show second countable, okay? Because first countable you need to deal with at every point and then every countable basis at every point. So let's talk about second countable here. How do you show that second countable is hereditary? Meaning you want to show what? And what do you want to show? Like back home. What's the statement to show here if you want to show that second countability here is hereditary? Give you the definition. What's the statement you want to show? If you want to show that second countability is hereditary. Give me the exact statement. Every subset of what? What property? What topological property is that? This one, I want to check out whether you can apply definition or not. What topological you are talking about now? I don't want to help. Sorry? What matrix was? I want what does it mean by say second countability axiom is hereditary? What does it mean? No need to find anywhere else, just here. Just this slide here. Why become products? I'm talking about talking about hereditary here. Gary want to help.
Every subspace of given that X is second countability, if you want to show that it's here, how do you pronounce that?
Hereditary.
Hereditary, then every subset of X is second countability. For example, having the countable basis.
Okay, so you need to replace this property with the property that you want to show. Okay, so if a second countability is hereditary, then every second countable space X, for every second countable space X, its subspace is second countable. Does it make sense? Hello. Hello. Okay. Okay. Yeah. If not okay, you can ask. Okay. Yes. Yeah. Topological property. What are you? What's your question? I haven't listened your question. I mean, you can ask whether a topological property is hereditary or not. For example, is compactness hereditary or not? Does every subspace of a compact space compact or not? Okay. Or every subspace of a connected space connected or not? Okay. Every what else? Closed subspace. Oh, sorry. Every subspace of a closed set is closed or not? Yeah. Okay. If it is, then we will say that that property is hereditary. If not, then no. Okay. All right. So let's prove one of the statement. So let's prove for second countable that is hereditary. Okay. So consider prove second countable is hereditary. So suppose since our space is second countable, so we have a countable basis for X. Okay. So what we want to show is there exists a countable basis for who? For what do you want to show here? How many is it? So what's our goal here? We want to show if I want to show that second countable is hereditary, we want to show that there exists a countable basis for all subspace of X. Okay. For all subspace of X. Can we find it or not? Can we find this countable basis for subspace A or not? Can we find it? Can we find it or not? How? You can simply take the collection of B intercept A. Okay, for B in B. Okay, you can show that this is the countable basis. Okay, for the subspace A. Okay, you can see from the subspace topology. Yeah. You need to know how to check why is it a countable basis. Because what's the open set in subspace A? Every open set that intersect with A. And then this B intercept A should be living in those intersections. Okay, because B is living in every open set in X. Okay, so you need to be able to write these little thing down, because this little things is checking whether you know the concept or not of basis. Okay. How about products? Let's say we want to show second countable is productive. Oh, this is part 2. This one part 1. Productive. How to show it? Again, suppose B is so BI. So we have need to consider product space or countable basis for xi. Okay. So what we want to show here, there exists a countable basis for product of xi. Okay, can we do this or not? Is this a countable basis? How do we do it? Product of all bases. Yes, yes. Because this is a product topology, product, yeah, product topology, not the box topology. So we take B to be the collection of all products of UI, okay, such that UI is in BI for finitely many I, okay, and for the rest of the UI, okay, it is equal to xi, okay, for all other I. Okay, and the claim here is this set is a countable set. This set is countable. Is it obvious why this set is countable? Why? Sorry. Before? When is it? Off. Finite union of countable set is countable. But here, this is arbitrary. Arbitrary product.
Because the rest is xi. It's really fixed. Because to that it's finite.
Yes.
And
Yes.
that is count.
Yes. 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 That's right. Yeah. Okay. Yes, that's right. This is how you argue. Okay. Because when you look at this product here, it's not every column will have countably many things. Okay. We are finite union of finite Cartesian product. You can think like that. Cartesian union of finite Cartesian product of countable set. Yeah. Union can go arbitrary union, is it? Union, yes, sir. Union can go arbitrary. Then okay, then we are good. Because we are arbitrary union of finitely many finite Cartesian space of countably many countable set. Okay. Yeah. So we put everything what we learned put together already. So you need to be able to use them. Okay. So let me write down here. So we said that this guy is a arbitrary union of finite product of countable set. Okay, so this guy is still countable. Yes, not the what. You here you still need to countable first, right? Countable, then here also countable, then everything countable. Okay. Okay, let's continue. So I mean, you can do the same proof for the first countability. Okay, first countability, just that you need to check at every point. Okay, it's a similar proof. You check at every point. Okay, let's continue. So what's good about this second countable here? So before that, we will define, actually, I think you saw this definition already in the assignment. So a subspace of a space X is said to be dense, in X if A bar equals to X. So whenever talk about this dense set, right, you should have a prototype in your mind. What's dense? What space is dense? Q. Okay, Q is dense is where? Ah, yes, because Q bar is R. Okay. Yeah, Q bar is R. All right. So let's see. What's nice about this second countable space? Okay, so suppose X is second countable. Then, so I'll give some definition along with this property here. Then X is what we call a Lindelof space. Okay, Lindelof space. So what space is this? Okay, so what property does this space hold? So that is, for every open covering of X contains a countable subcollection that covers X. Does this sound familiar or not? Sound familiar or not? Yeah, compact require finite, but here require countable. Okay, so you can go denumerable. Okay, so this is what called the Lindelof space. The other thing is X is separable. By the way, this separable has nothing to do with your connectedness. So what's this space to be separable? That is, there exists a countable subset of X that is dense in X. Okay, you already met one separable space. What's that separable space here? You already met it. What space is separable? R. R is separable, right? Because there exists a countable subset of R. What's that countable subset that's dense? Q. We just, so you see, everything we discuss is the same phenomena, but we just keep on giving new idea. Okay, yeah. Everything is a same example, but we keep giving new words, new notion, new idea. Okay. All right. So how do we prove it? So if it's second countable, then you are both type of cases. Second countable.
It means the first half.
Which one?
A.
Uh-huh.
The behind countably.
Mhm. Yeah.
Means the
You pick from this open cover here. That you pick this sub cover here from the open cover you started with. It depends on the open cover you started with. But no matter what open cover you have, you must have a countable sub cover. Yes. Okay, so what do we do? Let's prove it. So because our space is second countable, right? So we just let Bn, the set of Bn to be a countable basis for X. Okay, so this is how we work with the countable basis here. So A, so we want to show for all open cover, right? So we just simply take any open covering here. So the point is how you pick a countable subcollection here then. No, we only have second countable here. BA intercept A. I mean, this is the problem here. We want sub covering, right? So we need to use element inside A, but there's only countably many elements you can use. So how to find those countably many elements? This is a bit similar to the compactness proof. So Bn is a countable basis for X. What does this mean? Yes. Why? Because we can write our space as union of Bn. Okay. Then we simply choose An from A such that An contains Bn. Okay. Then so that X is equals to union of Bn, and then this union of Bn is equals to union of An. Okay. Does it make sense? Make sense or not? If don't make sense, meaning you forget what does basis means. Okay, go back and check what's basis. What property does this basis hold? Which one subset? This one subset? Yeah, this one is subset. Yeah, the other direction should hold as well. Okay, I'm hiding something here. I'm hiding something here. You need to, yeah, the other direction should hold as well. Why that direction hold is the argument that we use in the basis chapter. Is the basis chapter. So you go back on basis chapter because we are using it now. Okay, very important. This concept I cannot throw away because we keep using this basis of the topology. Okay, how about second part? There exists a countable subset of X that is dense in X. Okay, so how do we find this countable subset of X that is dense? So what do you need to do in this statement here? You need to first define the countable subset and then show that it is dense. Okay, two things you need to do. So where's the natural choice for this countable subset here of X? So meaning it is a subset of X, meaning everything in this set is an element in X. So you need to pick some countably many element in X. Okay, so where's the natural choice of this Sn here? what's the natural choice? Okay, I just pick any point from this Bn. Okay, I just simply pick any point from this Bn. See if it works or not. First of all, it's already countable now because Bn is already countable. Then I pick the point out of 1 point out of this Bn. And so my goal is to show that this set is dense. Okay, my goal is to show that A bar is equals to X. Okay, to show that this is true. So, what do we do here? So if you look at any point in X, what happened? What happened to this point in X here? Yes, so there's some bases that contain this point. Okay, but what happened to this basis? How to compare this basis with my set A? It actually intersect A. I don't know, because I pick. How do I pick? How do I define my A? I just pick 1 point from every basis element. Okay, this means what? Every basis element containing X intersect A. Meaning what? So X is in the closure of A. If you don't understand, this is definition only. So you need to go back definition. So that means when you come to this class, you need to keep your definition in your pocket. Okay, otherwise you will lost for sure. Because you lost for no reason. It's not you don't understand, it's just you don't know something. You get what I mean? You need to take your definition well with you. Okay, if you like, bring to bath, bring to sleep, bring to eat, if you are that kind of person. Some person is like that. OK， 需要苦读，有些人不需要苦读，很 smart 的讲一讲就会了。如果你是那种需要苦读的人，go ahead， 去做吧。OK， 你慢慢你就会 pick up 了。OK 了，不用一辈子这样做的，相信我。你只要 pick up 了过后，你就会变很快。但一开始你肯定是要让你自己去适应的，因为这是新环境，就是像幼稚园其实 OK， 你们是在纯素的幼稚园里面，真的，我就这样跟我的 MA1 的学生讲，你在幼儿园做你做的 exercise 是长怎样的？你在幼儿园的 exercise 是怎样的？怎样学？A 写100次 A， 100次 B， 100次 C， 100次大， 100次小， 100次水，写咯 ，proof 抄，先抄先抄到你觉得很顺了好像我懂他在讲什么了就这样，明白吗？就慢慢学上来哦。因为怎么讲Pure Max 还不是一个是很普及化的东西，所以我们没有把它普及到那种很下面。所以你们到了大学上来上这个纯素，不是？其实对你们来说是一个不能够新，但是是全新，是全新的东西。所以为什么很难就是这样？因为你已经这么大了，我还叫你做幼稚园的东西，是不是？所以变得很难哦。OK 了，Yeah，你就觉得哎呀，我怎么明明又会这样多了，怎么又不会了？现在你确实真的是不会，因为你没有上过这种东西，或者你也没有被 expose expose 过这种东西。比如说 Terence Tao 啊，Terence Tao 有人认识吗？Terence Tao，you know Terence Tao？UCLA 的一个 lecturer，他是澳洲长大的，然后澳洲第一个拿到 few medals，然后去美国了现在。你以为他数学天才，从小天才，他真的天才啊？你知道他爸是什么吗？他妈是什么吗？教授来的，所以他可能从小就被 expose 这样的概念了。这样，当然你说哦，人生赢在起跑线，可以赢在起跑线，但是你要知道啊，人生是继续的，不会停的。赢在起跑线可以跌在中途的，你明白吗？所以你要做什么？持续跑哦，如果你要的话啊，你明白吗？明白吗？OK，你只要持续跑，你就不会停。OK 吗？呀，说简单来说，就是不要遇到一点困难就放弃。OK 吗？呀，困难走过去啊，你就会觉得啊比较轻松啊。但是现在人不是有什么命吗？什么命啊？过了这个困难，还有更多的困难，something like that. But anyway，就是 life is like this 哦。So yeah, you can just deal it with locally 哦。如果你 globally 你不讲啊，我反正都要死，做这样多做么？你不是很奇怪，对吗？Something like that 啦，something like that，something along that line 啊。对，就是那种，yeah。一什么？我学生教我什么一时摆烂一时爽吗？啊，还是摆烂一时爽？Yeah, something along that line 哦。Yeah，对，没错。Yeah. OK，so 讲到这里说 definition 啊，把 definition 挖回来。OK，全部 definition 一定要挖回来。OK，example。OK，看一下什么 example。So we already talked about R is separable. Okay, R is separable. And also second countable, we have shown it already. Okay, because Q bar is equal to R. And another big example we want to talk about is this R with lower topology. What is lower topology? I still remember or not? What's the basis for lower topology here? Hmm. What's the basis for this guy? Half close. So yeah, half close. So where close, where open? Less close, where open. Okay. O A B. That's why we call lower because we close at the lower part. Can you define the upper or not? Try and do it. Should be okay, I guess. It's quite symmetric. Okay. And then how about this space here? First of all, this space is first countable. Why is it first countable? So what do you need to do for first countable? For every point, you need to find a countable basis. Okay. So let's say I give you a point X. So what's the countable basis you can build there? Yes. So X plus 1 over N. Okay. Okay. This guy will be contained in every neighborhood of X. And it's countable because we use this 1 over N thingy. And it's countable. So such that N is N. Okay, so unfortunately, this guy is not second countable. Okay, so how do we argue this? We argued it by contradiction. Okay, suppose it is. Okay, suppose on the contrary that B is a countable basis for R lower limit. Okay, the contradiction we want to get here is this B must be uncountable or not countable, in other words. Okay, not countable. So how do we get this contradiction here? How do we get this contradiction here? So, I mean, our space actually is uncountable. It's real number, right? So somehow you need to use the point inside the space here to help you get the contradiction. So let's see. For every point x, okay, we can find bx in B such that x is living in bx, and then this bx should live in the open set x2 x plus 1. Like this. Okay. If you have this kind of a bx, what do you think? You think? My claim is so the claim is if x not equal to y, then this kind of a bx shouldn't equal to by. Why? Because what? Because from construction, what do we have? X, yes, start from x. So how we say it mathematically, so we will say that x is actually is an infimum of bx, and y is an infimum of by. Okay. So they cannot be the same. Okay, if they cannot be the same, then from this bx by, we will infer that b must be uncountable. Okay, because for every point we can at least build this bxi. I mean for I index in R. Okay or not? We haven't talked about other bases yet. We just talk about this kind of basis. This kind of basis already uncountable, you know. Does it make sense? If you yeah. Yes. Hey, good question. What is basis definition? Yeah. Okay, we simply use basis definition only here. And then the point is actually the point of this neighborhood, right, is because we place the x at this close interval. It's not about this guy. This guy I can change to anything, right? S plus 100 also can. But the problem is I fix my x at this endpoint here. Yeah. If they're different, then this endpoint shouldn't be the same. You know. Yeah. Because how many different points you have in real number? For all these, for all these different points, I can have all sort of different Vx. So for this kind of Vx, I already have uncountably many due to the point I have in my space. If you like, then we'll say that therefore, since R is uncountable, B must be uncountable. Okay, I think this one better. Go up, go up, up.
Don't we only show one of the this is countable at first?
Yes, 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 yes. This Bx are chosen from this set of B. So far, so good. Okay. Okay. How about separability? Okay, is this separable or not? Okay, you actually can see that also Q bar is equals to RL. Okay. Use this new open set. New open set, which is this half closed interval here. Okay, you also can show that the limit point is everything. The limit point of Q is everything. Quite similar. Lastly, you also can show that it is Lindelof. Okay, what is Lindelof means? RL is not compact, right? But it's Lindelof. Okay, so meaning that every open covering of RL has a countable sub-collection. Okay, it's not compact, but Lindelof. Okay, so meaning you cannot find finite sub-collection. No? You need to hope for a countable sub-collection here. But you can reduce it to show that, instead of for every open covering, you just need to show for every open covering by basis element. Okay, remember last time we have this kind of reduction for compactness, right? We can reduce checking every open covering to just open covering by basis element. Okay, so every covering of RL by basis elements contains a countable sub-collection or sub-cover of RL. Okay, you can show this. And I think we don't want to do it in class. I'll put it inside the lecture notes. It's kind of a long argument there. You need to argue. Okay or not? Yeah. Okay, any questions so far about yes, compact B part B, yeah.
What if we are doing this, we are checking this for every counter loop.
Mm-hmm.
What if my basis is like X to X node? My basis contains all the elements X to X node. The basis is the collection of all X to X node. 它不在 X 到 X 这里。
Then 你就不是一个 basis 了，不是 ？Then you couldn't be a basis then. This is the basis property. This is the property of basis. Then you should be able to show that this is not a basis. What we use here is this is just okay. This existence here is simply property of basis. That's all. We don't care how this basis looks like, but this basis should do this thing for me. We don't really. So if you claim that this should be a basis, I think it shouldn't be a basis. Maybe you should check that this is not a basis. Yeah. Okay. Yeah. Good. Very good. Yeah. This is how you study maths. Actually, you need to question your definition. You need to question your definition. Okay. Because once you question your definition, you know what criteria I can put in, what criteria I can lift up, right? This is how you build new definition. Okay. If I put this extra condition, if I remove this extra condition, okay, they go to different routes. Okay, sometimes it's implied. Okay, sometimes it's implied, but sometimes you will get new things. Okay, yeah, it's good. You need to practice this. Okay, you need to play around with definition, is what I meant. Okay, otherwise you wouldn't know what you're doing. Okay or not? So for now, we will finish up this countability, and then tomorrow we will go into separation. And we'll talk about separation. All right, so see you tomorrow.